Okay, good morning. Can you hear me?
Yes, we can.
Okay, thank you. I hope that you had a nice break and now you have enough energy to continue our lesson. And one thing about the exam might be you have been worried about why I haven't corrected your exam papers till now. The reason is that unfortunately I forgot them at a school and I haven't been to a school from that time. So that's the reason that it has been delayed. I didn't want to go through unnecessary risk to go back to school. So on Monday I have to be in a school, so I will get your papers on Monday. Hopefully it will be ready by next Tuesday. Yeah, sorry for the delay. Okay, now I want to give two more examples. If I remember correctly, I haven't given you any examples related to this article, the primitive function. If you remember, we talked about primitive functions and we solved quite a few examples there. And then I told you that there are three articles that people mention when dealing with primitive functions. So one of them is they ask you find all primitive functions. So then it means that you need to show that you know the concept, and when you find a primitive function, you add a constant to it at the end. Sometimes they ask find a primitive function. So it means that you can choose whatever you want to for the constant c and just give us one primitive function. And of course, when that's up to you, I would recommend you to choose c equal to 0 because this is the simplest possible choice. And now I told you that there is also another article that can be used. If you see here, I have written it in italics. So here it means that you need to find a unique primitive function, but they cannot ask you to find the primitive function unless they provide you with extra piece of information. Okay, so this is one example that I want to solve. There is another example we will solve, and then we go to our new lesson, which is a very important lesson under the title of integrals. Okay, so determine the primitive function of f, the primitive function capital F of the function f of x equals to 3x squared plus 4x minus 1, such that the capital F calculated at minus 1 equals 2. Okay, the first thing that you need to do to solve this problem is to find all primitive functions first. Okay, so you would say that f of x is equal to 3x squared plus 4x minus 1. Okay, so from here, if I want to find all possible primitive functions capital X, what I have to do, I have to take the primitive function of the first piece. So if you remember, 3 is a constant, we don't do anything with that, and x squared, the formula is this, if you remember, x to the a, its primitive function is x to the power of a plus 1 divided by a plus 1, of course if a is not equal to minus 1, which is the case here. Okay, so let me just do it step by step. After a long break, you need to refresh your memory. So it becomes x to the power of 2 plus 1, which is 3, divided by 3. The next one I have 4. The power of x is 1, so I use the same rule. It becomes x to the power of 1 plus 1, which is 2, divided by 2. And then a primitive function for x, for 1, if you remember, is x. And then we put the constant c. Okay, and let us simplify that. So this means that capital F of x is equal to this 3 and that are gone, so I'm left with x to the 3. The next one, 2 and 4, are simplified. I am left with the 2 here, x squared, and then I have minus x but plus a constant c. This is the more or less I can call it a set, the set of all possible primitive functions to this function. But now we have been provided by an extra piece of information and we want to find it means that this should be unique. If I ask you how many functions you have found here, you would say infinitely many, one for each choice of C. Okay, so I have to use this piece of information here. What does this mean? This means that if f of minus 1 is equal to 2 means that if I replace x in capital F with this number, the answer is supposed to be equal to 2. Okay, so it means that instead of f of x, instead of x I put minus 1, and instead of f I put 2, and then you see that there will be an unknown left, and that is capital C. You solve that equation, find your C, put it back in your function, that would be your answer. So this is the strategy that we will use. Okay, so what I do, I put 2 equals to, I put minus 1 instead of x, and then simplify this. The left hand side is just 2, the right hand side is minus 1 plus 2 plus 1 plus C. That's a very unfortunate example. This happens to be 0, okay? Yeah. So this 1 and 1 are gone, and this 2 and this 2 are also cancelled. So I get that C is equal to 0. So that was a coincidence. Yeah, if you just find a primitive function with the older rule, you will find the same answer. But this is necessary to write down in the exam paper that you are finding that C. In the previous part we just randomly choose C equal to 0 because it was the simplest choice. But here this is not the case. We found that C has to be equal to 0 if this condition is supposed to hold. Okay, so then what happens here? What you need to write as the answer is this. You have to plug this back into the function that you found. You put C equal to 0 here, and then you get capital F of x equals to x to the 3 plus 2x squared minus x. And this has to be written as the answer at the end. Okay, if someone asks you what you have found as the answer, you would say that I found a function, or the function, whose derivative is this. You can check. If you take the derivative of this function, it becomes that. But not only this, if I put minus 1 instead of x, the answer would be 2. So that is the only primitive function equipped with that extra piece of information. Any questions? Good. Let me solve a little bit better problem here. So determine the function little f so that its second derivative is equal to this function, its first derivative at 0 is 1, and the value of the function itself at 1 is equal to 3/4. Okay, now I want to hear from you to warm up a little bit your brain cells. Okay, I hope that you are not sleeping. Anyway, can you tell me where should I start? Don't say that you don't have any clues where to start with, yes? Hello, can you hear me?
Primitive function.
Yes?
Yes.
Yeah?
Can you take the primitive function of f double prime?
This is the first step, thank you. So I would say that f double prime is equal to x squared plus e to the power of 3x. Okay? So let me just write this. Do you remember that if I have x to the power of a, its primitive function, capital F, is x to the power of a plus 1 divided by a plus 1. of course plus any constant, and we had also another famous function, exponential function. A primitive function for this is 1 over k. We repeat the function and then we put a constant. So these are the formulas that you had earlier, yes? Okay, so now I will do this one. If I go, now let me ask you one more thing. What is a primitive function for f double prime? If I take a primitive function from f double prime, I will go to the previous function, yes? So I will go to f prime. So this means that if I take a primitive function, if I take the primitive function from the left hand side, f double prime becomes f prime. Yes, because the derivative of f prime is f double prime, so by definition f prime is a primitive function for f double prime. Okay, and then what happens? A primitive function for x squared is 1/3 x to the power of 3, and for the next one, 1/3 goes down, and then I have e to the power of 3x repeated, but I have a constant c. Okay, but you see that this constant should be fine-tuned in a way that the derivative satisfies this given condition. So what does that mean? It means that if you go to your first derivative f prime and replace x with 0, the answer is supposed to be equal to 1. Okay? This will provide you the opportunity to fine-tune this c and determine that c exactly. So let us just do that. This is given that f prime of 0 is equal to 1. So this means that 1 is equal to 1 over 3 times 0 to power 3 plus 1 over 3 e to the power of 3 times 0 plus c. Okay, so this means that 1 is equal to, this one is 0, this one is 1, so it becomes 1/3 plus c. But I am looking for c, so I move 1/3 to the left, and it becomes 1 minus 1/3 is equal to c, so my capital C is 2/3, yes? So I was able to find the capital C. But when I found the capital C, I can put it back into the derivative function. So I would say, therefore, f prime of x is completely determined. It is x squared, 1/3 of x cubed plus 1/3 of e to the power of 3x plus 2/3. Okay, but this is just now the derivative. The question asks you about the function itself. So I think now it is clear what to do. I want to go from f prime to f, so I have to go through primitive functions once more, yes? So what I do, I will take a primitive function from the left hand side, it becomes f of x, and then it becomes a primitive function for x to the 3 is x to the 4 divided by 4. This 1 over 4 and this 1 over 3 will be multiplied, so it becomes 1 over 12 x to the power of 4. 1 over 3 is a constant. A primitive function for this brings another 3 down, 1 over 3 down, and then I have to repeat the function. So these two multiplied together gives me 1 over 9. And then I have e to the power of 3x, and then a primitive function for any constant, if you remember, is that constant multiplied by x. So a primitive function for 2/3 is 2/3 times x, but plus another constant, yes? So let me call this new constant d, not to mix it with the previous constant. Now you realize why the second piece of information is given to you, because you are also supposed to fine-tune this d so that the function satisfies this condition as well. So what does it mean? It means that if I go to my function and I replace, if I replace x everywhere with 1, the answer is supposed to be 3/4, yes? So this means that f of 1 equals to 3/4 gives me this. 3/4 is equal to 1/12, 1 to the 4, plus 1/9, e to the power of 3 times 1, plus 2/3 times 1, plus d. Then you see that everything is given except d. I should solve this equation and find d. Okay, so let us do that. So the left hand side is just 3/4. The right hand side, 1/12 times, this is just 1, this is also 1, so this is 2/3 and this is 1/12. 1/12 plus 2/3, so let us see what happens. So this becomes 1/12. I write it as 12/8. So it becomes 9/12, but 9/12 is 3/4. Yes? Okay, so this becomes 3/4 plus 1/9 e to the power of 3 plus d. Then I move everything to the left. Of course, you immediately see that when I move this to the left, it becomes negative and they are cancelled. And then I move that other term to the left, so this means that d is equal minus 1/9 e to the 3. So that is the d. But what you have to provide at the end for the answer is to plug this d back into the function. So this is your function so far, and you got that this is this one, so you put it back here. So the function that you are looking for is 1/12 x to the 4, and then you have plus 1/9 e to the power of 3x, and then plus 2/3 x, and then minus 1/9 e to the power of 3. So this is the unique answer that you should be able to get it. Okay, any questions? Okay, now we go to the new lesson. So in the new lesson we want to talk about actually integrals. And so even from ancient times, people were interested in finding the areas, especially at those times, to area of pieces of land. Yes, for obvious reasons, people were interested to be able to calculate the area of different geometric shapes. Okay, of course we have regular shapes like triangle, I don't know, parallelogram, rectangle, and everything like that. We know how to calculate the area of those things. Of course, the harder example would be how to calculate the area of a circle or the area of an ellipse or something like that. But the point is that of course if you have a piece of land, there is no guarantee that the borders of your land are very friendly to us. Yes, they can be different shapes, different curves. Some part might be a flat curve, some parts might be, I don't know, just a curve. So for example, you can imagine something like that, I don't know. Okay, so then you want to find the area enclosed between some straight lines and some curves. So what I'm trying to say is that the problem of determining the area of the plane geometric shapes was that actually very important, very interesting for the human from ancient times. Now let us take a step toward solving this problem. Okay, but we want to get close to this problem little by little, and of course you will continue this in Math 4. Okay, but let me start motivating you about the example. I don't know, I have decided to do some heavy calculations today. Some parts of it is in the book, I will mention them. Some parts of it are not in the book, but I want you to feel relaxed and try to see the calculations. I want you to be exposed to this calculation because I think it would be instructive for you. Okay, so here, what is the point? So let us just make it very simple. So here you see a curve, and that's a famous curve, y equals to x squared, and I have intentionally put this scale 1 to 2, so you see that each grid on the y-axis is 2 units, and each grid on the x-axis is 0.5, because I wanted to make it more flat so that things become more visible. That's the only reason. Okay, so for example, you see that when x is equal to 2, don't consider that this height is 2, this height is 4. Okay, on the y direction, every grid is 2 units. On the x direction, every grid is 0.5 units. Yeah. Okay, now the point is that we want to calculate, this is the x-axis, I want to calculate this area which is enclosed between this straight line and this straight line passing through x equals to 4 and this curve. At least this is not a trivial problem, yes? It is not a triangle, it is not a circle, it is not one of those shapes that we actually know how to calculate. By the way, Archimedes was able to calculate the exact value by a method more or less similar to what I'm going to describe, to calculate the exact value of this area, which is completely correct according to today's calculations. Okay, so the point is to calculate this area, and I hope that you agree that this is not a trivial problem, and then you can see it in this figure. So I want to calculate the area of this colored region. Of course, you can start counting the squares here. Of course, these are not squares, by the way, because the width is 0.5, the height is 2. So these are actually rectangles. But even rectangles, you can calculate the area easily, and then you can calculate the areas. There are some complete rectangles that you see here, but for example, this one is not a complete because one part of it is outside, and we don't know exactly how to calculate that bit. For example, the next one is the same. You see some part of it is outside the area that I am interested in, outside the region that I am interested in, so it's not a very good way to do that. The method that I want to describe it here for you is the method of a Riemann sum. Riemann is a brilliant German mathematician. Unfortunately, he died before 40 years. But he has done a lot of things before that age. So, yeah, he's very, very famous because of the discoveries that he has made and contributions he made for mathematics and physics, of course. Okay, so what we want to do, let me try to convince you of the method. So here, what I'm trying to say is that you take first this interval from 0 to 4, okay, and find the midpoint. The midpoint is 2, and then go up until you hit the curve, and then complete the rectangle here. Okay, so you complete this rectangle. Agree? So this is the method that I'm trying to tell you. So you, first of all, you consider the whole interval, you find the midpoint, from the midpoint you go up until you find the intersection point with your curve, and then here you draw a line parallel to the x-axis and complete a rectangle for yourself here. Okay? So this blue part, if I tell you, do you agree that the blue part, the area of this rectangle is equal to the area that we are interested in? Of course, it is clear even from this picture that no. This part is good, I need it. This part is a part of the area that I am interested in. But if I calculate the area of the rectangle, I am calculating this part which is outside of the region, and you see that this part that is inside the region is bigger than this part which is outside. So even in this picture you immediately realize that the area that you are interested in should be greater than the area of this blue rectangle. Yes? But at least it is a very rough estimation of the area below the curve. And of course you might laugh at the beginning, okay, this is very simple, I could do it myself. If my goal is to calculate the area of the rectangle and sell it to you for the area of this colored region, this is something very simple. Yes, you agree, but let us be patient and see how it goes. By the way, let us do the calculation. What is the area of the rectangle? I have one rectangle, so let me call it a rectangle. Let me change my color. So let me call area of rectangle number 1, if I have one rectangle. So you know that the area of a rectangle is the product of the height by width, yes? So if I ask you what is the width, you see that it's 4. And by the way, this is not a rectangle, this is a square here. If I ask you what is the height is also 4. So you calculate these two things, it becomes 16. Okay? So this is the rough estimation of the area of the region that I am interested in. Okay, so you know that this area number 1 is 16. Let me just calculate it here. And we can do something else. This is important for me to understand, that you understand. Okay, I will give some names to these things. The initial point, I will call it X node. The final point, here I have one rectangle, I will call it x1 here. And the midpoint 2, I will call it midpoint number 1. Okay? So always I want to denote the first label, the first number by x node. The last number x something. Here I have one rectangle, so I call it x1. And the midpoint, I call it mid m1. If I ask you, how can you calculate the area? Okay, how can I calculate the area in a different way? I want to write a formula for the area. So you see that I calculated this height. If I ask you what is this height, you say it is 4. It is from the picture clear. But if you don't have the picture, how do you calculate that this is 4? Can you tell me?
Put it in the function.
Put it in the function, thank you. You put 2 here in the function, it becomes 4. So what does it mean? It means that you are putting m1 into the function. Okay? And then you multiply this height, yes, by this width. This width is called delta x. Okay? So let me just denote it here. So from here to here, we call it delta x. So then it means that I multiply it by delta x. So of course I know that the area is 16, but I want to generalize this problem. I am not just interested in x squared, I am interested in all possible functions. So let me write the formula in this form. Is that understandable for everyone, what I have done here and what I've written? If it is not 100% clear, I hope that it becomes clear when I go to the next step. Now let me divide. Here I haven't divided the interval, I just started with the whole interval. Now I want to divide the interval into 2 pieces. Now we come up with this figure. Okay, so let me describe what I have done here. So I'm sorry, there is, I don't know, construction going on behind my window. I don't know, I hope that this is not very disturbing for you. So the interval from 0 to 4, this time I want to divide it into 2 sub-intervals. Okay, so from 0 to 4 I divide it by 2, so it becomes 0 to 2 and from 2 to 4. And I will do the same thing for each one of these sub-intervals. Okay, what do I mean by that? I mean I go to the first subinterval. So let me, by the way, name them as I did before. Again, I call this one x node, but this one is x1. This one now becomes x4. Okay? And now I go to the first interval and find the midpoint. The midpoint here is this one. Yes, I call it midpoint number 1. What I do, I go from this midpoint up so that I intersect my curve. So let me make it a little bit bigger. Okay, so I start from here, I go up to here so that I intersect. When I have that intersection, I complete my rectangle on it. It means that I draw a horizontal line from that point and I complete this rectangle. This I will call a rectangle number 1. Okay, so this is the way that I got this first blue rectangle. I do the same thing for the second interval. Sorry, I made a very serious mistake. I don't know why I jumped to 4 suddenly. x0, x1, x2. Yes, sorry for that. Okay. Now I do the same thing for the second interval. What does it mean? It means that I find the midpoint. This is the second midpoint, so I call it m number 2. And I do the same thing. I go up until I intersect the curve and draw a horizontal line and complete my rectangle on it. Okay, so in this way I got 2 rectangles. Even still you don't believe that. If I tell you that if I add these 2 rectangles, the areas of these rectangles, it becomes the area of the colored region, I think you agree with me. There is no guarantee for that. Okay, so what you see, yes, this part is in my region I need it. So far so good, but I am calculating an extra piece here. This cannot exactly compensate for this part, because even in this picture it is clear that this part I am hatching right now is a little bit bigger than that part that I have added. Yes, this part that I have ignored is a little bit bigger than this one, so they don't completely match. And the same is true here. If you consider this rectangle, what I have done, if I calculate the area, this part is good, okay, but this part again that I need is bigger apparently than this one that I am adding. So they are not exactly matching. But one thing I want you to have a feeling. If you don't, I will demonstrate it using Geogebra for you. What I am trying to say is the difference between the demanded area and the sum of the areas of this rectangle are getting closer. The difference between the real area and the sum of the areas of these rectangles become smaller. Okay. If I ask you how can you calculate the whole area, you would say that the whole area, let us do it exactly as I did before. Yes. So if I ask you what is area, the total area here is the area of the rectangle, the first rectangle, plus the area of the second rectangle. Okay, now if I ask you, can you calculate the area of the first rectangle? I have enough space, let me write in front of it here. Okay, so here I ask you what is the area 1 plus the total area, so let me write T total for, yeah, let me make it more clear. Total area of rectangles, okay? So what is this one? This is area number 1, the first rectangle, plus area number 2. But what can I write? Area number 1, I hope that you agree with me, this one is 2. If I ask you what is this height, by the way, this is 1. Do you agree? It is clear that this height is 1. So what I do, I write 1 times 2 plus, I calculate the area of this rectangle. I don't need to calculate the width is again 2, but the height this time is how much? Is 9, Why? Because if I put 3 into the function, it becomes 9. It is also clear in this picture, but you should not rely on the picture only. So you should be able to calculate these things analytically. So then it means that I have to write 9 times 2. And then it becomes how much? 2 and 18, 20. Area units, yes? So this is the one that I got, but let me write something similar to this one as a formula. This is important for our lesson today. I want to write this as a formula. So how can I calculate this area as a formula? So the area, let me call this area, by the way, let me call this one total A. So now A becomes equal to, this time each one of these are called delta x. So this is delta x, this is another delta x. Both of them are equal. Okay, now if I ask you, can you write a formula? The answer is clear. You have the midpoint number 1. If you want to find this height, you put this number into your function. So it becomes f of m1 times delta x plus f of m2 times delta x. Okay, so this is the total area of the rectangles, you see, not the total area of what I wanted to calculate. This is the total area of the rectangles. So is this formula clear for everyone? Okay, I can write this using sigma notation. So this becomes sigma. I can write I. So let me write k, doesn't matter. K goes from 1 to 2. Then I would write f of m sub k delta x. This sum is called the Riemann sum. The Riemann sum was only one term in the first situation. Now it is 2 terms in this new situation. So this is a sum. You see, this sigma is a sum. But of course, this sum, if I ask you what is this 20, you would say that this is a better, a more reasonable approximation to the area that I am interested in. Hopefully you agree with me. This 20 is a better approximation than this 16. Yes? Because the differences between these areas that I am ignoring and the areas that I am adding for no reason there, they are closer together this time. Okay, now let us go to the next situation. The next situation, I want to divide it to 3 pieces, but calculation for 3 pieces is a little bit hard. Let me go first to 4 and then come back to do the calculation for 3. The reason for 3 is not very good because you need to work with fractions. Why is that? Because now I am dividing my interval to 3 subintervals. So it means that the whole length, which is 4, I have to divide it by 3. So this number we have to calculate, this number we have to calculate. Okay, so the midpoint I have to calculate. I will come back to it, not because it's very different, but because the calculations is a little bit messy. I don't want to distract you right now, but let me just immediately jump. But I can show you something here. At least you see when I go to 3 rectangles, this area is not calculated, this area is not calculated, this area is not calculated. But on the other hand, this area is calculated, and then you see that they are getting closer, these bits, yes? And this bit is more or less very close to this one, and this bit is more close to that one. So hopefully you agree with me. If I add the areas of these 3 rectangles this time, I am getting an even better approximation to the real area. Now let us go to number 4. To number 4, you see that is exactly this case, and still you see that there are some parts that I haven't been able to calculate by adding the areas of the rectangles, but these bits that I am ignoring are actually getting smaller and smaller. You see the difference between this one and that one is actually, I think if I remember here in this case, this is more or less the exact value. So I don't remember exactly. But anyway, you see that the differences are getting smaller. Okay, now let us do this calculation here. This is what I want you to understand. So let us do some notation. The first point is, again, I call it x node. How many rectangles I have? I have divided the whole interval into four partitions, yes? So this one, the next point is x1. The next point I call it x2. The next point I call it x3, and the next point I call it x4. This is just a coincidence that when this is 4, this is also 4. The reason that I have from x node to x4 because I have partitioned my interval into 4 equal pieces. But now if I ask you what is delta x, each one of these are delta x. Delta x is a smaller. Okay, and now if I ask you how did I found this first rectangle, the idea is the same. This I concentrate on the first subinterval. I find the first midpoint, so let me call it M1, and I do the same thing. Let me make it bigger for you to see it. So I go from here up. When I intersect this point, I complete my rectangle. This is this narrow rectangle that you see. I go to the next midpoint, I go up to find the intersection, I complete the rectangle. That is the way that I found this rectangle. I will do the same thing here. I find the midpoint, I go up, find the intersection, complete the rectangle. So that's the idea is the same. So here you realize that this is the second midpoint, this is the third midpoint, and this is the fourth midpoint. So if I want to do the calculation here, what happens if I ask you what is A here? Let me make it a little bit smaller now. If I ask you what is the total area of the rectangles, here I have 4 rectangles to add. Okay, so what is the area of the first rectangle? What is the height? Can you tell me what is the height of the first narrow rectangle here?
Mm.
1 over 4.
1 over 4, yes, because f of x is x to the 2, so you put 0.5 here, 0.5 to the power 2 is 0.25. So the height is actually a quarter, exactly. So let us just do that. So this becomes 1 over 4. So let me write 0.25 multiplied by the width is equal to 1 unit. Hopefully you agree with me. What is the height of the second one? Again, can you tell me? I think it's better to write with fractions. It's easier to work with fractions in this case. So it is 1/4. So what is the height of the second one? This one. It's 9 over 4. Why? Because 1.5 is 3 over 2, and you give it to your function, it becomes 3 over 2 to power 2, so it becomes 9 over 4. So 9 over 4 is of that one, so it becomes 9 over 4. And the width is again equal to 1. All of them are equal to 1. And then the same story here. This is 5 over 2. I put it in my function, 5 over 2 to power 2, it becomes 25 over 4, so that is 25 over 4 times 1. And then finally I will have the other one, which is 3.5. 3.5 is 7 over 2. If you give it to your function, it becomes 49 over 4 times 1. But times 1 is actually unnecessary, so I add them. 1, all of them have the same denominator, so I add them. 1 plus 9 is 10. 10 plus 25 is 35. And 35 by that, what is the answer? 35 plus that one is 84 divided by 4, yes? Am I right? Please watch my calculations and then it is how much? 42 divided by 2 is 21. So what I get is 21. So what I get in the first one, you see I got 16. In the second one I got 20. I increased to 4 units. I dropped this one. I haven't not done the calculation, but you see that it is not increasing that much even from the second step. It was 20, now it is 21 units. Okay.
How much? It was 74 over 4.
Ah, okay. Thank you. Thank you. Thank you for that. 74 over 4. Thank you. So it becomes 74 over 4. Let me calculate it once more. This is 10, 35. So I don't see that is correct. What you are saying? Isn't it 84?
It is 84.
Let me calculate again. 1 plus 9, 10, 35. I consider this 50. 50 and 35 is 85. Yeah, I did it correctly. I think so. So this becomes 21. Oops. It becomes 21 area units. Yeah, my calculation, I think it was correct, but thank you for helping me. Yeah, it's very good to watch my calculations because sometimes I write something wrong. I realize later. Okay. Now, but let me do it once more. I want to write it as a Riemann sum. Okay, what should I write? This is clear and it is very straightforward. What I need to do, instead of writing 1 over 4 in general, I should write f of m1 delta x plus f of m2 delta x plus f of m3 delta x and finally plus f of m4 delta x. You see that all of these terms have the same structure, so I can write it again as a sigma. I can write f of m sub k delta x and then I run k from 1 to 4 in this case. Okay, so I think it's better not to spend that much time on the other one, but here the midpoint, so let me just give you the highlights. So here this is x node, this first one is x1, this next one is x2, and this one is x3. Here I have 3 rectangles. So from here to here this time is delta x. The same is true for this one. The same is also true for this one. All of them are delta x. But if I ask you what is delta x, how do you calculate it? Okay, I don't, because you see that they are not exactly passing through the grids. Can you tell me what is the value of delta x in this particular example? 4 over 3, because you say that the whole length, so let me write it intentionally like this. So you say that 4 minus 0, I have divided it into 3 pieces, so delta x is equal to this number, which is 4 over 3. Okay, now can you, but the midpoint is not very trivial here. Can you tell me what is the first midpoint? Okay, let me ask you one question. Can you, x node, what is x node? X node is 0. Can you tell me what is x1? 4 over 3, exactly. You have 0 plus delta x. Yes? Which is 4 over 3. If I ask you what is x2, you say x2 is what? Is x1 plus delta x. Yes? So it becomes 4 over 3 plus 4 over 3. But intentionally I want to write it in a different way. Instead of x1, I can write 0 plus delta x and then another delta x. So it becomes 2 delta x, which is of course the same, 8 over 3. And if I ask you what is x3, you say x3 is the previous one, x2, plus another delta x. Okay, but what is x2? x2 is 2 delta x, so it becomes 3 delta x, and it becomes 4. Yes, so that's clear, it should be 4. And now can you tell me what is the first midpoint?
4 over 6.
Yes, how did you calculate that? So the first midpoint is the left hand side x naught plus the right hand side point divided by 2. Yes, so what would be the answer? As you said, 0 plus 4 over 3 divided by 2, so it is 2/3. And if I ask you what is the second midpoint, you go here, the second midpoint, so you see the first midpoint is somewhere here, so let me just show it in the picture. So this is the first midpoint. The second midpoint is, it's in this picture it is clear, it is 2. But if I want to calculate it, I need to add x1 and x2 and then divide by 2. x1, I calculated it already, x1 is 4 over 3. What is x2? x2 is 8 over 3, and then I add them and then divide by 2. If you do this calculation, it becomes 2, as it is clear coincidentally in this picture. And then you can continue. Okay, so I hope that I can convince you somehow about this. This is my whole goal. Okay, the colored area is approximately equal to a Riemann sum. Are you somehow convinced? Of course, I can convince you more by demonstrating these things on Geogebra. I will do it shortly. But hopefully you agree with me. The colored area that I was looking for is approximately equal to a Riemann sum. How can I improve this approximation? Can you tell me now? I want to test your understanding. How can I improve this approximation?
You draw more rectangles.
I draw more rectangles. Exactly. But can you tell me, drawing more rectangles, how is related to the delta x?
Same principle as area of a circle, I believe.
No, I'm asking you. You told me that I have to increase the rectangles. Increasing the rectangles, how does this affect?
More precise.
No, I'm asking you this question. Increasing the rectangles, how does this increasing of rectangles affect the value of delta x? When you increase,
x becomes smaller.
Becomes smaller. Thank you. When you make the rectangles more and more, you are making delta x smaller and smaller. So it is clear. Let me ask you another question. So the number of rectangles, you see, the number of rectangles, let us call it n in general. So in general, a Riemann sum is this: sigma of f m sub k delta x. K goes from 1 to n. N is the number of intervals, yes? The number of subintervals. So you said that I need to increase the number of rectangles. Increasing the number of rectangles means increasing the number of subintervals. It means making delta x smaller and smaller. Okay? So let us demonstrate this idea using Geogebra here. Okay, so we go to Geogebra. I have already programmed Geogebra, so that is the area that I am interested in calculating. Now this is 0 rectangle. I press 1. This gives you the first rectangle. And look here. Is that clear, by the way? Do you see Geogebra screen or not? Okay, so this little a you see, which is in blue, is the area of this rectangle. Do you remember we calculate the area of the first rectangle here? It was 16. Do you remember? Okay, and then let us go back here. So when I have only one rectangle, this area is 16. This b that you see is the real area that I am looking for. Of course, the Geogebra doesn't give you the exact answer. I don't know why. This is the approximate answer for the area that I am looking for. Okay, so you see, I am far away from this. Let me increase the number of rectangles once more. Now what's happening, you see the calculation was correct. So the sum of the areas this time is 20. It's getting closer to the real area. Let me increase this more. We skipped this calculation if you remember, but what is the this is the picture. And now let me make it 4. We calculated. Do you remember? We got exactly 21. Do you remember? So this is the area of the rectangle. It's getting very close. Already we are very close to the real value. You see, the real value is 21.33 something, and then we are actually getting 21. So that's not that bad, even for 4 rectangles. Now I didn't do the others one. Let me increase number 5. You see what's happening? Look at these numbers and look at these pictures, okay? We are getting even closer. So let me increase this. You see, I'm getting closer. Now let us make it be extremely high. You see? And let me turn off the grids here so that you are not mixed. So unfortunately sometimes this work is strange. I don't know which. Okay, so let me turn off the grids. Okay, so you see 34, you already, of course still your eyes can detect the difference between the areas of the rectangles, the sum of the areas and that part, but let me increase this one. You see, so this is up to 100. Still I think we can detect it. Let me see if I can increase this range. Yes. So let me make it up to 1000 this time. Let us see if it works. Yes. So now let me increase it even more. You see, it's already 300. Now it is hard to detect the difference, at least for an old man like me. Might be you still can detect that, but then let us increase that to more and more values. I don't think that you can now realize, but we are I don't know, around 470. Around 170. These are those rectangles that are adding together, but they are so fine that you see them continuous. So let alone if I increase it, I don't know, to 1000, so it's even more smooth. So I think now you agree by this demonstration that this idea, even though is boring to start writing the areas of the rectangles and adding them one by one, but it seems it is in principle it works. Okay? Now I don't know, are you convinced or not somehow that this is a good trick, even though it's really boring? We have done it with computer 1000 times, you know, but let's assume that we want to do it by hand, okay? And then by the way, you see, if I do it 1000 times, up to 4 decimal points, there is no difference at all. Of course, if I can, I don't know, let me see if I can set the GeoGebra. I don't know, this GeoGebra somehow is good, but sometimes it is, I don't know how I should go to setting here now. This is classic number 5. Classic number 5 is better in some cases, but worse in the other cases. But let us see if I can increase the precision of GeoGebra. Do you know how to do it? There should be some setting somewhere here. Settings, so advanced. No, I don't know exactly where it is. So okay, might be here. There is some place that you can ask GeoGebra to calculate things more precisely. In Classics 6 I knew where what is, but in Classics 5 I've lost where it is. I don't know. Anyway, okay, might be here. No. Do you see any precision or something? No. Anyway, I don't know exactly where that is, but what I wanted to say, let us see that when it starts. No, so here you see there are big differences. Still, you can detect the difference up to 75 rectangles. If I increase the rectangles, I see the difference. Difference can be viewed. And now, let us, yeah, here, 265 rectangles. These two numbers match up to 4 decimal points. So if I iterate this for 265 rectangles, up to 4 decimal places, I get exact value. Okay? And then of course you see that if I increase it, no, it's not distinguishable at all. It seems continuous. Okay, now let us go back to the theory. So now can you formalize this? Can you tell me how to write the formula for the area? Can you help me to do that? So you see that this is an approximation. No matter how big I make this n, of course I get better and better approximations. But can you tell me, in principle, it is not practically possible, but imagine, if you want to make it 100% equal, what do you do? Can you tell me? I told you it's not practically possible, apparently, but it's intuitively clear what we are supposed to do.
You have to make infinitely many.
Exactly, infinitely many rectangles, which is practically a little bit absurd, yes, because how can I do it? But let us not worry about that one. I would say that the colored area, so let me write it with a different color, the colored area is equal to the sigma k goes from 1 to infinity f of mk delta x, but people doesn't write up to infinity because infinity is not a number. They write limit when n goes to infinity. Okay, so that is my goal. I wanted to convince you, at least on paper, this makes sense. Now please tell me, do you think that this makes sense for you as well or not?
Yes.
Yes. Okay. Remember, in this demonstration, I didn't go up to infinity. I just did 1,000 times. 1 billion, 1 trillion, I don't know, all of these. Infinity is even bigger than those things. So, yes, I think on paper, it's completely intuitively clear that this is a reasonable definition or reasonable calculation of this colored area. You see, you don't see any track, because if you remember, I started with this brownish area, and when I increase, you will still see a little bit of brownish thing under the curve, but when I increase it, actually you don't see any brownish area because they are so close together that they are filling up all those gaps that it was clear when I have a little bit lower number of rectangles. Okay, is that clear for everyone now? But there is a very big obstacle for this formula. Can you tell me what's the obstacle? I actually implicitly mentioned that.
It takes a lot of time.
Yeah, not a lot of time. In principle, even if you have a supercomputer, they are not capable of doing something infinitely many times. They can do it, for example, 1,000 times, 1 million times, 1 billion times, but not infinitely many times. But the situation is not that bad. Okay, at least Archimedes was able to do this, okay, at those times, exactly. And he was a real genius, by the way. So I want you to see what are the obstacles. I want to present a simpler example for the time being, because I don't think we can finalize it in 20 minutes for this problem. But let me choose a simpler problem. Try to solve the problem using this formula that we got here. I don't know. You didn't see what I wrote? Did you see when I wrote this formula?
Yeah.
Okay. So here I want you to use this formula to calculate a very simple area that you already know the answer to, and to see that yes, even though it seems useless, but it is not that useless. Okay, and then I will do a more heavier calculation, which is not included in the course, but I insist that you see it. I will calculate this area today, this area, okay, using exactly the method that I described here. The calculation becomes very heavy, but I want you to sit relaxed as if you are watching a Hollywood movie and try to enjoy the calculations, okay? This is at the level of your knowledge. I can describe it in a way that you can understand it, but it's not mandatory at all. But I will believe that this is really instructive if you see it once. Okay, now today I want to solve a simpler problem for you, okay? I want to solve this problem. I will take this graph, the graph of the function. Instead of y equals to x squared, I want to make it even simpler. Y equals to x. Yes, of course, it also goes from this direction. So let me consider this one, and let me concentrate only from 0 to 1, okay, from here to 1. So let me exaggerate a little bit. So 1, 2, 3, 4, 5. Let me consider this to be 1, okay, because I want the picture be big so that you can see that. Okay, my goal is to calculate this area. Of course you know how to calculate the area without these kind of fancy things. But I want you to calculate the area in the new method and compare them. Okay, first tell me what is the calculate. So here is 1. Here is 1. What is the height? Can you tell me?
1.
It's also 1. So what is the area? So the area is 1 times 1 divided by 2, which is 1 over 2 area units. So this we know. Let us see if we can confirm this number using this fancy method today. What should I do? Let me make it a little bit bigger. What I do first, I divide my interval from 0 to 1 to n equal pieces. Okay, so now what is delta x? Can you help me to write delta x? What is delta x if I divide my interval to n equal pieces? Hello, what is delta x? What is the length? What is the total length? 1. If I divide it into 2 pieces, each piece is 1/2. If I divide it to 3 pieces, each piece is 1/3. If I divide it to 4 pieces, each piece is 1/4. Now I am dividing it into n pieces. So what is delta x? 1 over n. Agree? Yes?
Yeah.
Okay. Now, if I ask you, let me concentrate on one of these subintervals. So the subinterval from xk minus 1 to xk. This is just one of them. Okay, I haven't drawn the other ones. Okay, let us concentrate on this one. So the midpoint is this number. Okay, so let me call this one midpoint number k. And then what should I do? Let me change the color. You need to go up, intersect this, complete your rectangle. Okay? This is the thing that you have to do here. Okay, so what is mk? Mk is the middle point here, so it is xk minus 1 plus xk divided by 2. Yes? This is mk. What is your function, by the way? Your function f of x is equal to x. You see, y equals to x. Okay, now can you tell me what is xk? Xk, how many delta x's I need to traverse to reach to xk? So do you remember? Let me go to this picture. Here, if I want to reach to the first point, I have 1 delta x from x naught. If I want to reach to x2, I have 2 delta x's. In this picture, if I want to reach to x2, I have 2 delta x's. When I want to reach to x3, I have 3 delta x's. Here, if I want to reach to x3, you see I have 3 delta x's. So it is very clear, hopefully. If I ask you what is xk, xk is k times delta x. But what is delta x? Delta x is this one, so it becomes k over n. And if I ask you what is a sub k minus 1, for the same reason, it becomes k minus 1 times delta x, and it becomes k minus 1 over n. Do you agree with me? If you don't agree, please shout, okay? I will continue because I want to finalize this problem. Now I calculate mk for you. For calculating mk, I have to add xk minus 1 and xk and then divide it by 2, yes? Okay, so what is mk? Mk is equal to 1 over 2. What is xk minus 1? Is this expression. Plus, what is xk? Is this expression. Okay, so the denominators are the same. So let us make the common denominator k minus 1 plus k. Yes, and then I have a 1/2 here. So you see this becomes 1 over 2n. K and k becomes 2k minus 1. So this is my mk. Agree? Now, what is the Riemann sum? Let us show you. The Riemann sum is f of mk times delta x. So if you don't mind, let me take this with me to the next page. If it works, yes, it is working. So let me put it here somewhere for you. And make it a little bit smaller. Yes, so we can put it here. So this is the formula. So far, what I need? I need delta x. I did it. What is delta x is here. I needed fmk, I found it, it is here. The next step is to calculate f of mk. So what is f of mk? Can you help me, make me happy? So what is f of mk? What is f of mk?
MK.
It's mk itself, because f of x is x, so f of mk is mk. But what is mk? I found mk. It is 1 over 2n, 2k minus 1. So now everything is clear. What I do, so I would write that the area is equal to the limit n goes to infinity, sigma k goes from 1 to n, f of mk, which is this expression, multiplied by delta x, which is this expression. And let me simplify this a bit. 1 over n and 1 over 2n can be multiplied and written simply as 2k minus 1 divided by 2n squared. And k goes from 1 to n, and n goes to infinity. Okay, so not very simple, but you see that we got this limit. The main problem is how to calculate this limit. I want to motivate you how to calculate this limit. Remember that n is getting extremely large. So what I do, because you don't know that much sigma symbols, so, the properties of those, so let me get rid of sigma symbol. How should I do? I want to expand the sigma. How should I expand the sigma? I need to replace k with 1, so it becomes 2 times 1 minus 1 divided by 2n squared. I intentionally don't calculate the numerator. Then I put k equals to 2, so it becomes 2 times 2 minus 1 divided by 2n squared. Then I put 3 and add all of these things, yes? Minus 1 divided by 2n squared. And then we continue until we reach to n. Please let me know if you don't understand what I am doing. I am just expanding this sigma. Expanding this sigma means replace k with 1, replace k with 2, replace k with 3, and continue until you replace k with n and add them up. Do you agree with me? Okay, so silence means probably yes. And then this becomes the limit. Now the good point is that all of these fractions have the same denominator. So I put the same denominator for me, but this is exactly at the level of your knowledge. I hope that you are not scared from the calculations. You should love it. Okay, so how should I calculate the numerator? Do you have any idea? This is a Math 1C problem.
It's an arithmetic progression, right?
Yeah, it's arithmetic progression. If I write it, so let me write it in this way. How many minus 1s you see here? I have n of them. So it becomes minus n. Minus 1 plus minus 1 plus minus 1 up to plus minus 1 n times. So it becomes minus n. Then there is a 2 here, a 2 here, a 2 here, a 2 here, so I can factor a 2 out. The first one becomes 1, the second one becomes 2, the third one 3, up to n. Yes? And then n goes to infinity. Very small steps left, we are done. I hope that, as Dylan said, this is an arithmetic progression. This is the very famous formula. Arithmetic progression. If you have forgotten, let me just write the formula here for you. So it becomes 2. The formula for this package is n times n plus 1 divided by 2. Okay, and then I have minus n divided by 2n squared. N goes to infinity. Okay, then what happens? This 2 and that 2 are cancelled, so I will be left with, and then I multiply n inside. So it becomes n squared plus n and minus n divided by 2n squared. N goes to infinity. But this n and that n are cancelled, so I get limit of n squared divided by 2n squared. And then now n squared is cancelled, so it becomes the limit of a constant number when n is going to infinity. The limit of a constant is a constant. Yes? And you see that this answer we got is what we were able to calculate simply by the rules of the triangle's area. Yes? So even though, you see, I was able to do it infinitely many times using mathematical concept of limit. I didn't actually do it infinitely many times, but I used the idea of here. Actually here I didn't calculate the limits at all, because the limit, the function becomes a constant function. So this is the simplest possible case. I think later it's also good to know about the other problem that Archimedes solved and I stated today. It is more cumbersome to calculate to the real value, but at least the reward is that you get something that you don't know. Here you already know how to calculate the area of a triangle, so why should I bother about this? But about the problem that I started with, we don't know. So if we do this, we find the exact value. But let me, before finalizing today's lesson, let us see why after primitive function we jump to this topic. What is the connection? The connection actually was discovered by Newton. Newton realized that instead of doing this heavy calculation, instead of calculating this Riemann sum, there is another alternative, but you need to be genius to discover that. Yes, he said, do this. Find a primitive function for your function. A primitive function. Everyone, what is a primitive function for x? Everyone, what is a primitive function for x?
X squared divided by 2.
X squared divided by 2. Newton said do this. What is the initial point 0? What is the final point 1? Put these two in the primitive function. Okay? If you put 1, it becomes 1 to the 2 over 2. It becomes 1 over 2. If you put 0, it becomes this. And then subtract these two numbers. And you get your answer. Okay? So this was invented or discovered by Newton actually. This is the main important thing that we want to come up here. Okay? So this method sooner or later will fail. The reason is that you see that the reason we were lucky. Here we came up with a series here with a sum that we know how to calculate the sum. But because this happens because the function was so simple. In the next example, the function is x squared. You will see that you have to calculate such a thing, which we don't know. This is no longer an arithmetic progression. Calculating these sums become heavier and heavier and totally impossible for generic function. Let us, for example, if I have sine function, then I will have sine functions, the sum of sine functions. I don't know, you can have a lot of complicated functions. I want you to feel it, that the obstacle against this method, of course this is very lengthy, but that is not the real obstacle. The real obstacle is to calculate this is impossible most of the time. So this is why in principle this trick is correct, but it is very limited. Okay? And if it is not limited and you can calculate, you see it is really tedious. And this method of Newton is actually very brilliant. So this is why we started. Do you remember I told you that assume that finding a primitive function is just simply a mathematics game, but now it's more than a game. Because if you know how to find the primitive function for a function, then you can immediately calculate the area using this idea. So the primitive function is connected to the area. So it means that you go from the game of finding primitive functions to game of finding the areas. Okay? But of course, finding the areas are very good. It might make you very rich by selling your lands or something when money comes into the game. But at the end of the day, money is also a game in this life, isn't it? Okay. So I hope that you have a good understanding of what's going on. None of these calculations are necessary for this course at all, but I really find it very instructive if you can feel the difficulties of calculations. Then you would appreciate the genius of Newton. That okay, now you can simply calculate it like that. Here, this is a little bit more lengthy than here because it was so simple. But if I make this function a little bit harder, this method does not work at all because we don't know the area of those shapes. And this method will work, but it will destroy ourselves we will destroy ourselves if we want to calculate everything here. And the important thing is that sometimes it becomes impossible, but it is still possible to use this brilliant idea of Newton. Okay? Okay, thank you very much.